In this question, we're presented with 100 blood donors with the following distribution of blood types. The question is asking for the probability that a random donor will have blood type AB. Because the question doesn't specify whether this donor is Rh positive or Rh negative, we can conclude that there are going to be 4 donors out of 100 who are going to have blood type AB, or in other words, 4%. So the answer here is A. This question is asking us for the probability of getting 3 6s if we roll 3 dice. So the probability of rolling 1 6 with 1 die is simply 1 out of 6. And so with 3 die, that probability is going to be 1 out of 216. So the answer here is going to be B. This question is asking us for the probability of getting a sum of 8 if we roll 2 dice. Okay, so this is a little bit more involved, but basically the thought process behind this is to think about all the different ways in which you can get a sum of 8. And because the numbers only range from 1 to 6, we have limited possibilities. So you can have 2 plus 6 or 6 plus 2. You can have 3 and 5 or 5 and 3. And lastly, you can have 4 or 4. Okay, so that's out of a total of 36 possibilities, right? So there are 6 total possibilities on each die. You square that to get 36. So 1, 2, 3, 4, 5. 5 possibilities out of a total of 36 possibilities. And so we see that the answer is C. So this question is asking us about the probability of drawing a 3-card sequence exactly. And this is from a standard 52-card deck. It actually doesn't matter what 3 cards they are for this question. What you have to realize is that there's only one way to get that particular 3-card sequence. And we have to calculate the number of total possible 3-card sequences. So because there's only one possibility, 1 goes in the numerator, and the total number of 3-card sequences, well, before you pull your first card, you have 52 cards available. Okay, so it's 1 out of 52 essentially. Then after you pull your first card, there are only 51 cards left. After you pull your second card, there are only 50 cards left. And so your calculation becomes 1 over the product of 52 times 51 times 50. And so we see that the answer here is letter D. So this question is asking us about how many different 5-card combinations are possible if you draw 5 cards from a standard deck. And the question specifically clarifies that you do not care about order. So in this situation, you can directly apply the choosing function. Okay, the choosing function, the formula for that is n factorial over n minus r factorial times r factorial. Okay, so n factorial, the n here represents the total number of cards in the deck, so that's 52. And you're pulling 5 cards from that deck. So it's going to be 52 minus 5, or 47 factorial down here, times 5 factorial. So n is 52 here, and you're choosing 5 out of 52. So r is 5. Okay, so we see that the answer is, in fact, solution D. This question reads, what's the probability of getting 4 5s in a row when you roll a die 4 times? Okay, so the thought process is that there's only one way to get 4 5s. So that's going to be in the numerator. In the denominator, you want to have the total number of outcomes. And because each die has 6 faces, you have 6 choices each time. Of course, you're going to roll that die 4 times. So it's going to be 1 over 6 raised to the 4, or 1 over 1 to 9 6. So we see that the answer is C. One other way of thinking about this, right, is to take each die individually. So if you roll a dice 4 times and you want 4 5s in a row, there's only 1 5 on each face. So every time you only have a 1/6 chance of rolling a 5. and you're going to do that over 4 times. Again, this is going to give you the same answer, but it's just another way of thinking about the problem. So this question reads, a randomized crossover trial involves 4 interventions. Each participant will get each of the 4 interventions in a random order. How many possible orderings of interventions are there? So this is simply 4 factorial. So 4 factorial is going to equal 24, and we see that the answer is B. Now the reason this is 4 factorial might not be immediately obvious at first, but basically the question's asking for the possible orderings of 4 different interventions. So basically imagine you have intervention A, intervention B, intervention C, and intervention D, right? So it's asking us how many ways can you order these 4 letters. So when you first pick your intervention here or your letter, you have 4 choices. So I'm going to put 4 here. Then after you pick your first one, whether it's D or not, you have 3 choices left. So you're going to pick, so I'm going to put 3 here. And so you can see if I follow that logic, I'm going to result in this expression 4 times 3 times 2 times 1, which is simply the same thing as 4 factorial. So this question reads, when you draw 3 cards from a standard 52 card deck, what's the chance that you will get a 3 of a kind? Okay, so this is a little confusing at first, but let's break the problem down into pieces. So the first thing I'm going to do is to think about what I want to be in the fraction. Okay, so in the top, in the numerator rather, I want to have the different number of 3 of a kind hands. Okay, so all sort of the winning hands of getting 3 of a kind. And in the denominator, I want the total possibility of 3 card combinations. Okay, so the denominator is going to be 52 choose 3. That's saying I choose 3 cards from a 52 card deck, and that's going to be all the possible 3 card combinations. Okay, and so that's going to equal 22,100. Now let's think about the numerator again. So for each type of card, of which there are 13 types, right, there's 4 choose 3, so 4 ways that you can get a 3 of a kind. So there are 4 times 13, or 52 different 3 of a kind hands. So then the fraction becomes 52 over 22,100, or answer choice C. Okay, so this question reads, a certain lottery works by picking 5 lucky numbers from 1 to 47 and 1 mega number from 1 to 27. And you only win if you match all 6 numbers. Okay, so basically you have a condition for the first 3 numbers and then a new condition for the last number. So that's one way of thinking about it. So how many possible combinations are there for the first part of picking 5 numbers? So that's going to be simply 47 choose 5, which is equivalent to 1.5 million, about basically. Okay, so there are 1.5 million possible 5-number combinations for the lucky numbers. And each of these, right, each of these combinations, each of these 5 numbers can be combined with one of 27 different numbers from that mega number. So the total number of ways to win is 27 times this number, 47 choose 5. Okay, and that works out to be about 41,416,353. So how many ways are there to win? Only 1. So this is your answer, and that corresponds to answer A. So this problem introduces the at least type problem. And just as review, for at least type problems, the key is to realize that the probability of at least of the event happening at least once is equal to 1 minus the probability of it not happening at all. Not at all. Okay, so the question reads, if a couple has 5 children, what's the probability that they have at least 1 boy? again, so you're clued into this fact that it's an at least type problem because of the wording in the question. What's the probability that they have at least one boy? So this probability is represented by the probability of doing 1 minus the probability of no boys at all, right? So that's equal to doing 1 minus, and it's 50%. 1 minus 50% raised to the 5. And it's raised to the 5 because the couple has 5 children. So you do 1 minus 0.5 raised to the 5, and that works out to be 0.969, or about 96.9%. So answer choice D is the correct answer here. In this next problem, we're given a situation where the probability of some situation B is 0.75, and the probability of some situation A is 0.2. And then we're given this joint probability of A and B as 0.1. And we're being asked if A and B are independent or not. So if A and B are independent, then the probability of A happening times the probability of B happening is equal to this joint probability. Okay, so we can check whether they're independent or not by multiplying 0.75 times 0.2, which works out to be 0.15, which is not equal to 0.1, and so we say that they are not independent. The correct answer in this case is A. This question reads, suppose that 15% of the population was exposed to some dangerous chemical Z. So if you're not exposed to Z, you have a lifetime risk of some bad thing happening of 0.0001. And if you are exposed to Z, your lifetime risk increases fourfold to 0.0004. So what percent of the population will develop this really bad thing? In this problem, it's pancreatic cancer. And so the way of doing this is to just use the law of total probability, which is just a fancy way of saying weight the percentages. So if 15% are exposed and their risk, right, is 0.0004, you want to add that to the 85% of the population where their total risk is 0.0001, right, and just add these two to get the overall risk in the overall population, and this works out to be 0.000145. So the correct answer here is answer choice D. This next question presents us with a similar situation. So 15% of the population is exposed, which means 85% are not. Those that are exposed have an elevated risk of 0.0004 of developing pancreatic cancer. Those who are not exposed have a fourfold lower risk of 0.0001. The question is specifically asking if someone develops pancreatic cancer, what is the chance that he or she was exposed to Z? So this is probably easiest illustrated through a diagram. So there are two branches here. You can either be exposed to chemical Z or not exposed. So your probability of exposure is 15%. Your probability of non-exposure is 85%. If you're exposed, right? So if you're exposed, the probability of developing disease is 0.0004. If you're not exposed, the probability of developing disease is 0.0001. And I'm just going to subtract to fill out this branch and this branch. I'm basically going to just subtract by 1. So this branch is going to be 1 minus 0.04, and this branch is going to be 1 minus 0.0001, because that's the probability that's left over. So another way of thinking about that is that these probabilities have to sum to 100 at every juncture, right? So if I multiply this out, I get 0.00006 here, and if I multiply this out at the bottom, I get 0.000085. Okay, and these are what we're interested in, because ultimately what we want to do, right, remember, is to calculate the probability that a person was exposed to chemical Z, given that he or she develops pancreatic cancer. And the fact that this person, he or she, develops pancreatic cancer is represented by these two probabilities. Okay, so the probability of disease given exposure, which is this, over the probability of disease when you're not exposed, plus the probability of disease when you're exposed, right? So that's going to be the sum of both of these numbers. So this is the expression that we are interested in, and this is equal to 41.4%. So if you have pancreatic cancer, there's a 41.4% chance that you were exposed to this bad chemical. So in this question, we're given a fictitious probability of event B, which is 0.75. We're given a fictitious probability for event A, which is 0.2. And then we're also given a probability for A and B, this joint probability of 0.1. Okay, and the question is asking, what is the probability of A given B? Well, the probability of A given B, there's a formula for this. You can do the probability of A and B over probability of B. You can think about it like you're dividing out this probability of B. And so that, of course, is equal to 0.1 divided by 0.75, and that is equal to 0.133. And so the answer in this case is answer A. In this question, we're given a few clues, and we're being asked to select the correct statement about sensitivity, specificity, and positive and negative predictive values. So let's read the question first. So in a group of patients presenting to the emergency room with ankle pain, 30% of them have a fracture. 60% of patients with a fracture are older than 55, and 30% of patients without a fracture are older than 55. So what this kind of information immediately lends itself to is making a contingency table, or a 2x2. Because we're dealing in percentages, we can just make up a baseline number of patients at 100. This is going to make things easier. So we're told that 30% of patients presenting with ankle pain have a fracture. So if we make this row fracture and this row no fracture, 30% of 100 is 30, which makes this row 70. Now the columns are going to be age, let's just make this greater than 55, and we can make this less than or equal to 55. Okay, so next part, 60% of patients with a fracture are older than 55. So of the 30 patients that comprise these two cells, 60% lie in the top right cell. Okay, so 0.6 times 30 is going to equal the number in this cell, which is going to be 18. That automatically makes this one 12. Then the next clue, 30% of patients without a fracture are older than 65. So 30% of 70 is going to be the number in this cell, and that's going to be 21, which is going to make this cell 49 just by subtraction. Then I'm going to add vertically to fill out this 2x2. So once we have this 2x2 set up, we're basically done with the question. So looking at this 2x2, you can calculate the negative predictive value. The negative predictive value, of course, is the number of true negatives over testing negative. Okay, so basically of all the people who tested negative, how many were actually negative? That's what this is getting to. So that's going to be 49 over 61, which corresponds to answer D in our question.